I welcome you for this presentation. In this presentation, we are going to discuss about digital signatures. This is the overview of this presentation. That is introduction to digital signature, then the basic digital signature model, then attacks and forgeries in the digital signature, then digital signature requirements, direct digital signature method, Elgamal digital signature method, Schnorr digital signature method, then digital signature standard and digital signature algorithm, followed by summary of this presentation. So far we have looked about the message authentication scheme. In the message authentication, what we are doing is we are securing the two parties from the third party. That is, any third party is interrupting in between the communication of Alice and Bob, then we can easily identify using the message authentication. But if there is a dispute occur between the sender as well as receiver, whoever is involving in the communication, then how to handle that? Because suppose Alice sends a message to Bob and Alice claimed that I didn't send a message, and also Bob also claimed that I didn't receive any message from Alice. Likewise, some disputes arise between the sender as well as the receiver, then message authentication won't provide a solution. It is to provide some solution for some third party exploitation, not among the sender as well as receiver. Suppose if there is a dispute between sender and receiver, then we must have or we have to provide a solution. For that only digital signature comes to a picture. That is, we are verifying whether the sender only sends the message to a concerned receiver or the receiver receives a message from a corresponding sender. So, in order to solve the disputes rising between the sender as well as the receiver, we are going in for the digital signatures. Because all the methodologies look somewhat similar only, you have to know the basic difference between message authentication and digital signature. So, what the digital signature is providing is, it is providing the ability to verify the author, date and time of signature. Then it authenticates the message contents and it is verified by third parties to resolve disputes. So these things are provided by the digital signature. So it is included in the authentication function with some additional capabilities. It is also for message authentication, but in order to solve the disputes between sender and receiver, we are just maintaining or verifying the author as well as the date and time of the signature of both the sender as well as receiver. That is for digital signature. Let us see the digital signature model. This is the digital signature model. Here, how digital signature is generated and transmitted from the sender to the receiver. Here, Bob is sending a message to Alice with a digital signature. So, the message M is applied to the digital signature generation algorithm, and using the help of Bob's private key, a signature is generated, that is Bob's signature for the message M, and the message with the signature S is sent to Alice. And Alice, upon receiving the message as well as the signature, Alice is generating a signature from the message using Bob's public key and verifying whether the generated signature as well as the signature received are same. So if it is same, they are returning that Alice is returning that the signature is valid. If it is different, Alice is returning is as not valid. So this is the communication, generating a signature, then communicating along the communication network and receiving by the receiver. Here exactly what Bob is doing and what Alice is doing. So what Bob is doing is, so if message is applied to a given to a cryptographic hash function, and the hash of this message is generated, and using Bob's private key, this hash is encrypted and you are generating the signature. Yes, here then only with this message as well as the signature is sent to Alice. So upon receiving this message, what Alice is doing is again using the messageium, malice is creating a hash of this message using the cryptographic hash function, then comparing, then with the digital signature also, Alice is decrypting that using Bob's public key. Then H dash is generated and comparing both H and H dash. If both are same, then Alice is telling that the signature is valid. If it is different, Alice is telling that it is not valid. So this is the basic digital signature format. So if the sender or the receiver denies that they didn't send a message or they didn't receive a message, in such cases, if any third party is coming in to resolve a dispute, then they can easily solve the dispute. Whether they send the message or not, they can easily find out. The third party can easily find out. Let us see what are the different types of attacks and forgeries possible in this digital signature. The attacks are key only attack. That is, if the attacker knows only the key, then how the attacker is performing the attack. Another thing is known message attack. If the attacker gets some of the earlier messages, using that how the attacker is performing some attack. Then generic chosen message attack. That is a general message is chosen, and based on that how the attacker can perform any attack. Then directed chosen message attack. Directed chosen message in the sense the attacker has to specifically in the earlier case it is a general thing, that is generally some message he is sending, but in the directed message the attacker is specifically taking some choosing some message and performing the attack. Then adaptive chosen message attack in the sense the attacker is generating an oracle in the sense if the attacker knows earlier message and signature pairs, using that message and signature pairs the attacker requests the sender of the message to give some thing, and based on the message, based on that content, that is earlier message signature pair content, the attacker is choosing something from that and performing the attack. That is the adaptive chosen message attack. So these are some of the attacks possible using this digital signature. Next is some how they are breaking the digital signature. Means one is the total break. Total break means fully they are breaking. That is the attacker is getting the private key of the victim. In that case it is a total break. Next is the selective forgery. Selective forgery in the sense attacker forges the signature of a particular message chosen by the attacker. That is whatever the message, only a selective signature of a particular message is selected in order to forge all the contents. Existential forgery in the sense the attacker forges the signature for at least a single message. For if the attacker is performing an attack for a single or forges something for a single message and getting the control of the full messages, then it is called as existential forgery. So this existential forgery is of a minor nuisance only, because they are performing or taking a single message signature only, no. So it is some of the minor nuisance to the victim. But the total break and all are giving more nuisances to the victim. So these are some of the attacks and forgeries. Next is the digital signature requirements. So always the digital signature must depend on whatever the message signed, and it uses the message information unique to the sender. That is in order to prevent both forgery as well as denial. That is the sender or the receiver may forge something, that is modify the content, or sometimes they deny that they didn't send. So these digital signature requirements, that is whatever the information we are sending must be unique to the sender in order to prevent both forgery as well as denial. Then must be relatively easy to produce. Another thing is digital signature must be relatively easy to recognize and verify. Whatever the algorithm we are using, digital signature algorithm, that algorithm must easily recognize the digital signature and can verify the digital signature. And very important thing is it must be computationally infeasible to forge. That is, with a new message for existing digital signature, it has to it must be computationally infeasible. Then with fraudulent digital signature for a given message also, it must be computationally infeasible to forge. Another thing is we have to save the digital signature in some storage systems, then only we can verify it easily. So these are some of the requirements of digital signature. Next is the direct digital signature scheme. This is the basic digital signature model. Here, both the sender as well as receiver are involved, and we are assuming that the receiver has the sender's public key. In the digital signature model also, we have seen the signature is decrypted using the public key of the sender only. So we are assuming that the receiver has the sender's public key. Then digital signature made by sender signing entire message or hash with the private key, and we can encrypt using receiver's public key also. The important thing is that we have to sign first, then encrypt the message as well as the signature, and mainly the security depends on the sender's private key, because how we are generating the signature using only the sender's private key. So the security depends on the sender's private key only. That only plays a vital role in this digital signature. So coming to the earlier one is the basic digital signature methodology. Next is Elgamal digital signature. We already seen about Elgamal public key crypto system. There one peculiar characteristic is there, that is the ciphertext produced by the Elgamal public key crypto system is a pair. In other crypto systems and all, we are getting a single ciphertext, but in this Elgamal crypto system, we are getting ciphertext pair. Likewise, in this Elgamal digital signature also, we are getting a pair only. This is a signature variant of Elgamal related to the Diffie-Hellman. So here also we are using exponentiation in the Galois finite field. Here it is providing security based difficulty of computing the discrete logarithms as in Diffie-Hellman. So there also we have faced one difficulty, that is computing discrete logarithms is difficult in this Elgamal public key crypto system. Here in this Elgamal digital signature also the same problem we are facing. And here in this Elgamal digital signature, it uses a private key for encryption, that is in order to perform signing process, and it uses the public key for decryption, that is in order to verify the signature. So each user, that is example, generates their key, that is chooses a secret key number that lies between 1 and q minus 1. Then they are computing the public key, that is ya equal to a power xa mod q. Then Alice sends a message M to Bob by computing the hash M of the message. This M equal to H of M. M lies between 0 to Q minus 1. Then they are choosing a random integer K that lies between 1 and Q minus 1, and always the GCD of K comma Q minus 1 is 1. That is, it must be relatively prime. The key, the K value as well as Q minus 1 is relatively prime to each other. Then we have to compute the temporary key. That is, temporary key means here S1 equal to a power k mod q. That is, we are computing S1 equal to a power k mod q. Then we are computing k inverse. You know how to compute the inverse value. So k inverse equal to inverse of k mod q minus 1. Then we are computing S2 values. That is k inverse m minus xa into S1 mod q minus 1. Likewise, the signature is generated. It is a signature pair S1, S2. So in the Elgamal public key crypto system, we have generated a ciphertext pair C1, C2. Likewise, in the Elgamal digital signature, we are generating a signature pair, that is S1, S2, using the above given formula. Then any user can verify the signature by computing V1 equal to a power m mod q and V2 equal to ya power S1, S1 power S2 mod q. So if the signature is valid, both V1 is equivalent to V2. Both V1 and V2 are same. If the signature is not valid, we are getting a different value for V1 as well as V2. So this way only we have to verify the signature using Elgamal digital signature. Let us see one example. So here we are using a Galois field of 19, that is q equal to 19 and a equal to 10. Then how Alice is computing the key? A chooses XA equal to 16 and computes YA equal to 10 power 16 mod 19, which is 4. And Alice signs a message with a hash value, that is M equal to 14 as 3, 4. That is, they are choosing random K equal to 5, which has the GCD of 5 and 18 is 1. Then Alice is computing S1 equal to 10 power 5 mod 19 equal to 3. So we are having the S value as 3. Then Alice is finding K inverse mod Q minus 1, that is 11. Then computing S2 values, that is 4. If you apply the formula, you are getting 4. So what is the signature pair? That is S1 comma S2. The signature pair is that is 3 comma 4. That is the signature pair. So if we apply the signature pair to verify the signature, that is V1 we are getting a 16 and V2 we are getting a 16 mod 19. So both V1 equal to V2. V1 and V2 are same. So the signature is valid. If we are getting different value, then the signature is not valid. So you have to see whatever the steps involved in generating a digital signature, that is in the Elgamal digital signature, we are generating signature pair. Always you have to keep this in mind. We are generating signature pair, and in the verification process both V1 and V2 must be same. If we are getting the same value, then only we are telling that the signature is valid, otherwise it is not valid. Next is Schnorr digital signature. It uses exponentiation in the Galois field only. Here also the security is based on the discrete logarithms. Here also computing the discrete logarithms is difficult compared to similar to that of the Elgamal digital signature. So here this scheme minimizes the message dependent computation, that is multiplying a 2n bit integer with an n bit integer. So main work can be done in the idle time only in the Schnorr digital signature. It uses a prime modulus P, that is P minus 1 has a prime factor Q of appropriate size. Typically P 1024 bit and Q is 160 bit numbers. Generally it is used. So how the key is set up in the Schnorr digital signature is, we have to choose two primes P and Q, and we have to choose a value A such that A power Q congruent to 1 mod P. And here A, P and Q are global parameters for all. And each user, that is A, generates a key, that is Alice chooses a secret key number SA that lies between 0 and Q, and compute the public key VA equal to A power minus SA mod Q. This is the key setup phase. Then the signature is generated. User signs message by choosing a random number R, that is R lies between 0 and Q, and computing the value of X is equal to A power R mod P. Then concatenate the message with X and hash result to compute E equal to H of M concatenated with X. That is the hash value is computed. That is the E value. Then they are computing Y equal to R plus SC mod Q, and the signature pair is generated. Here also in the Schnorr digital signature also signature pair is generated. Here also it is very, very important. The signature pair comprises of E value as well as the Y value. Both values, E and Y value, forms the signature pair in this Schnorr digital signature. Any other user can verify the signature as follows, that is X dash equal to A power Y V power E mod P. Using this, they can verify, any user can verify the generated signature using Schnorr digital signature. Another thing is digital signature standard. It's a very famous thing. So US government approved this digital signature scheme. It is designed by National Institutes of Standards and Technology and NSA in the early 90s, and it is published as FIPS 186 in 1991. And the revised versions of this digital signature standard happened in 1993, 1996 and 2000. This digital signature standard uses the very famous hash algorithm, that is Checker hash algorithm. And here digital DSS is a standard, digital signature standard, and the corresponding algorithm is DSA, digital signature algorithm. So FIPS 186-2 2000 includes alternative RSA and elliptic curve signature variants, and DSA is a digital signature only, unlike RSA is a public key technique. So here this FIPS includes an alternative to RSA and elliptical signature variants, but DSA is a digital signature algorithm, but RSA is a public key technique. That is the difference between DSA as well as RSA. Don't confuse with this. It is a digital signature algorithm. RSA is a Rivers-Shamir-Edelman. It is a public key crypto system. There is a difference between digital signature and public key crypto system. All of you are aware of that. So here this is the pictorial representation of RSA approach as well as the digital signature standard approach. So what in the RSA it has happened means the message is passed to the hash function, and hash of the message is generated and it is encrypted using private key of A. Then message as well as the encrypted hash value is concatenated and it is sent to the receiver. That is, there we are receiving the message as well as encryption of the private key of A comma hash of the message M. Then from the message the user is generating or the receiver is generating the hash value and comparing with the received hash value, that is decrypted using the public key of A, and they are comparing both the hash value and the received hash value with the message, both are same, then they are telling that it is correct, otherwise it is not valid. Then coming to the DSS approach, what they are doing is they are generating a signature using the hash value. They are not performing any encryption. They are generating a signature using the public key of G as well as the private key of R. Then it is concatenated with the message and it is passed. So here you see M comma the signature pair SR is there. Then using that from the message H is generated. Then it is S and R are verified using the hash value generated using the M, and it is compared, and if it is same then we are telling that it is a valid, otherwise it is not valid. So this is the difference between DSS as well as RSA. Let us see the digital signature algorithm. It creates a 32-bit signature with a 512 to 1024-bit security, and it is a very smaller and as well as faster than RSA. RSA is a public key crypto system, but it is a digital signature. The DSA is a digital signature algorithm. So it is to generate the digital signature. So it is a digital signature scheme only, and the security depends on the difficulty of computing the discrete logarithms. In all the digital signature scheme, the security depends on the difficulty of computing this discrete logarithms only. It is a variant of digital signature algorithm, is a variant of Elgamal as well as Schnorr scheme. So whatever the methodology applied there, it is some of some delta variation is there only in this digital signature algorithm. So how we are generating the key using this digital signature algorithm means here we are having the shared global public key values, that is P, Q and G, and the sender is choosing a 160-bit prime number Q and also choosing a large prime number P with 2 power L minus 1, that is P ranges from 2 power L minus 1 to 2 power L, where L equal to 512 to 1024 bits and is a multiple of 64. Such that Q is a 160-bit prime divisor of P minus 1. Then we have to choose G equal to H power P minus 1 divided by Q, and H lies between 1 and P minus 1, and H power P minus 1 by Q mod P is greater than 1. And the user chooses the private and compute the public key, that is they choose random private key, always X is less than Q, and they are computing the public key Y equal to G power X mod P. You can compare all these three algorithms, that is whatever the algorithms you see, Elgamal, then Schnorr and digital signature algorithm. You just draw a table for these three algorithms, and if you write these steps, then you can easily find out the difference between these three algorithms, and you can easily remember these algorithms also. So how the signature is created in this digital signature algorithm is, they are generating a random signature key, that is K. K is less than Q. Very important thing to note is K must be random and it is destroyed after use and never be reused. So key is a one-time key. And then computes the signature pair R equal to G power K mod P mod Q, S equal to K inverse H of M plus X of R, XR mod Q. Then we are sending the signature R comma S with message M. Already we have seen the block schematic of this digital signature algorithm. So you please draw a table stating that first is a Elgamal digital signature, then Schnorr digital signature, then digital signature algorithm. What is the key generation phase? Then what is the signature creation process and what is the signature verification process? Write these things in a table, then you compare these steps. Only minor changes are there, and always we are generating digital signature pair. That we always have to keep it in mind. Not only in Elgamal, in Schnorr as well as digital signature algorithm also we are generating a digital signature pair. Then how we are verifying the digital signature means using digital signature algorithm, that is we receive the message M as well as the signature pair or comma S. In order to verify a signature, the recipient computes W equal to S inverse mod Q, then U1 equal to H of M into W into mod Q, U2 equal to RW mod Q, V equal to G power minus U1 into Y power U2 mod P and mod Q. If V equal to R, then signature is verified. If it is not equal, then the signature sent or received signature is not a valid signature. This is the overview of the digital signature standard. That is whatever the steps we have discussed, the same thing only explained here. That is the message, using the message hash of the values created. Then with the key F1, how we are using the F1 function as well as F2 function. The input to F2 is key, then P, Q and G, and we are generating R. Then with the using the F1, we are just giving the hash value, then key K value. Then output of F2, then X and Q, and we are providing S, we are generating the S value. Then we are sending the message with S and R. Then we are comparing whether both are equal or not. If it is equal, then we are telling that the received signature is a valid one. So in this presentation, we have discussed about introduction to digital signature, then digital signature model, then what are the attacks and forgeries possible with this digital signature, then some of the requirements of digital signature, then we have seen some schemes like direct digital signature, then Elgamal digital signature, Schnorr digital signature, then digital signature standard as well as the algorithm. So we have discussed the difference between message authentication as well as the digital signature. Main thing is digital signature is to avoid the disputes or solve the disputes between the sender as well as the receiver, among sender and receiver, not from the third parties. Thank you.